Okay, I am going to get started at this moment. Right, so welcome once again to ECS 173, and we are continuing in our first module of the course, which is about analyzing photographs. So we have thus far talked about the very lowest level of image description in terms of its Fourier transform. We've talked about how to remove noise from imaging data and how to detect edges and corners. So now, again, we're moving from very, very concrete properties of imaging data to things that are more abstract or more cerebral or more further removed from numbers that you read off of your digital camera. And today we're going to talk about something called saliency, also known as detecting regions in the image that are interesting in some general sense. So in particular, we're going to focus on one technique that I kind of like for this problem of detecting salient regions. And the reference is there. It's from one particular paper. But there's also a set of slides that I'm going to post to SmartSite that's a great presentation that's put together by a colleague of mine about other ways to detect interesting regions in images. And I'll tell you sort of what I mean by interesting as we get started here. So if you recall from Friday, I showed you this pair of images. And just for a second here, I'm going to turn off the one remaining light because it has these little tiny red dots on it that kind of go away completely if there's any light shown. So what I told you is that there's this thing called the Harris corner detector, whose purpose in life is to detect corners in photograph, where a corner is supposed to mean the usual thing of maybe something that's at a 90-degree angle with a dark spot inside and the rest of it is kind of bright around the outside. But what it ends up doing in practice, the way it gets at this, is it tries to find regions in the image where there are two dominant gradient directions. So if you pool all of the pixels from this little region together, you will find that it's not the case that there's no gradient, and it's not the case that there's one dominant gradient direction suggesting an edge, but there's two dominant gradient directions. And we showed how to figure out whether there's 0, 1, 2, 1 or 2 gradient directions using the eigenvalues of the gradient. Now, what I'd like to suggest to you, though, is that if you run one of these Harris corner detectors on an image, the spots that will light up as being so-called corners will not really correspond to your semantic notion of what a corner is. In fact, what it ends up doing is finding spots in the image where something interesting is going on. And so in particular, notice that out here in the background, we never seem to detect any corners. And by the way, the corners are these red, where all these red spots are. But where it does find corners are in places where there's something going on, where if you were to look at this, close your eyes and then open them and look at this image for the first time, your eye might wander to these locations in the image. So on the flatly shaded back of the cow, it's flatly shaded. It's kind of not a lot of information there. But around all these contours, there's information about the kind of shape of that blob of black stuff on the cow. So that's what we mean. What do we mean by interesting region? Well, it's not well defined, but we will talk about one way that one approach has defined it. But in general, I just said this, but we're moving our way up this ladder from low-level features of the image to higher level, more semantically meaning stuff, and this is where we are right now. So previously, last week, we tried to ask ourselves the question of, are there edges in the image, and are there corners in the image? And now we're moving up to something that's a bit more ill-defined, maybe a little bit subjective, maybe a little bit more abstract, saying, what are the interesting regions of the image? So By the way, when I use the term salient or interesting, those are kind of synonymous in my mind. So let's start out by asking ourselves the question, what does this term salient mean? Well, you know it when you see it. Humans are infallible for detecting what features of imaging data pop out with respect to the background. And this is kind of the idea of interestingness, is that it's the part of the imaging data that pops out with respect to the background. And I don't have to tell you what it is about each of these 4 examples that is salient. You can all figure it out on your own. You know it's the green square and the not filled in circle and the edges that are not in the right direction and the thing that isn't a square. None of them use the same exact cue or the same exact characteristic to pop itself out from the background. It could be color or orientation or shape. But in any case, you can always tell what it is. You know it when you see it. And it turns out that this is true in a very literal sense. If you attach so-called gaze tracking equipment to your face, what these things do is they basically use a set of half-silvered mirrors and cameras and sometimes infrared light sources pointed at your retina to track where your eyeballs are moving when you look at stuff. And then you present the person with this piece of equipment attached to themselves a new photograph or a new piece of visual information. You can actually track where their eyes go as they are scanning or evaluating this new piece of visual information. And it turns out that your eyes do this so fast that it's not conscious. You don't realize you're doing it. It's part of your hardwired visual system. So what you should notice right off the bat is that, oh, and by the way, what we're doing here is overlaying on top of this newspaper and that Google printout, or that Google page, where the person who was looking at it, where their eye was looking. So everywhere where you see black, you're looking at the trajectory of this person's eyeballs as they're moving around. So what you should see is that the human visual system, as it has been hardwired by years and years of training and thousands of years of evolution, it somewhat picks up what you might consider to be the most important or interesting aspects of both the newspaper and the Google printout. In particular, it seems to scan the headlines. It kind of identifies very quickly that it's a person in the photograph just by stopping on the 2 eyeballs. What's the most important? When you look at www.google.com and you enter some search terms, the most important place to look is not over here, and it's probably not even down here, but it's up here. And so I'm kind of dodging the question of how exactly to define interestingness in any kind of absolute sense, only to say that you know it when you see it. And it depends on the context. The reason why this is a practical thing to worry about in image processing is that defining interesting regions can actually speed up image processing a lot. And I'll show you what I mean. There's a whole set of problems in computer vision, aka image processing, that can be formulated in terms of finding correspondences between local regions in one image and local regions in another image. So when I say local regions, you can think of the term patch, or a little sub-image, or a little image region. It's the thing that's inside the green triangle or green rectangle there. And generally speaking, there's a set of problems where one image can be referred to as something like the model, and the other image can be referred to as something like the scene, or the input image to your image processing system. And what you're trying to do is establish correspondences between regions in one and regions in the other. And so what this does is it does what the arrows show. It sets up an identification between a region here and a region there. And if you're wondering what problems this might why it might be useful to think of image processing problems in terms of this construct, well, here are some examples. If we have 2 views of the same object taken from different points of view, I think I mentioned this one time last week, that what you can do, if you can identify that one location in one image, such as right here, is the same thing in the world as another pixel in another image, then what you can do is use your information about where those two photographs were taken and triangulate to figure out where this thing is in the real world. And if you can do that throughout this image, then you can basically reconstruct the 3D structure of the objects in the image based just on a set of photographs. This is one of the really bread and butter problems in image processing. It's called structure from motion, aka multi-view geometry. And the reason why you might want to do this should be pretty obvious. I mean, the killer app for this is that you have a video camera and you're a tourist and you're walking around this church and you just you just walk around it while you're pointing your camera at it. And then you take the video and you put it on your desktop computer. And you grind and grind and grind away. And the next thing you know, you've got a full 3D model of this thing you went to see on your vacation. But now, the underlying problem that is really the thing you have to solve in order to do this triangulating thing is that first step, which is identifying that a particular location in one image corresponds to a particular location in another image. And this just shows some examples of spots that are in correspondence across these images. So this local region here corresponds to this local region here. This local region here corresponds to that local region there, and so on. So this is one example of the general problem, or one instance of the general problem of setting up correspondences between local regions in one image and local regions in another. The same idea applies to tracking objects in video. So this is something that comes up a lot in things like sports, for example, and also advertising and games and things, where what you want to do is for each frame in a video sequence, for example, of somebody playing ping pong, you actually want to identify what pixels in the first frame correspond to what pixels in the second frame. And so, for example, I want to be able to identify that these pixels here correspond to these pixels here, and that these pixels here correspond to these pixels here. And if I can do that, I can again do that structure for motion thing and build up a 3D model of this guy as he's moving and going through a ping pong shot. I can also do some kind of neat things like automatically blue screen, which is to say automatically remove from the video all the stuff in the video except for the guy playing ping pong, so that you can then superimpose your own background behind that, so that he's suddenly playing ping pong on a yacht or in the middle of the jungle or what have you. And in fact, there's even less frivolous examples of why this is a useful thing to do. You can actually analyze someone's motion as they're doing something like a ping pong shot and figure out the biomechanics of how they are moving their muscles and how they are flexing to make this action of ping pong, of hitting the ping pong paddle. And in fact, one of the places where this is actually used in practice is golf. Because there are enough people who play golf who have enough money to spend on it that they really want to do the biomechanical study of how their swing works and how they can modify their swing to make it basically hit the ball farther. So anyways, but again, driving all of these applications is the underlying problem of establishing correspondences between a set of pixels in one image here and a set of pixels in the other image. Finding region correspondences is also at the base of probably so basically in computer vision or in image processing, the two problems that take up the bulk of the literature are detecting objects in photographs and structure for motion. So this is the other problem, which is object detection. So given a photograph, the kind of holy grail problem is to automatically detect that some object that I already know about, like this cornflakes box, is present in the image and it is in a particular location like right here. This has numerous applications. The most boring and practical one being being in manufacturing, where your factory is producing a set of widgets or objects of some type. They are rolling down a conveyor belt, and you want to be able to tell automatically that one of them has a defect in it or not. And furthermore, you want to be able to tell how many of them you are actually producing as they are flowing by in the conveyor belt. And it should be fairly clear that agriculture is just like a hop, skipping, and jumping away from that, where you have picked thousands and thousands of peaches and they are flowing down the conveyor belt, and you automatically want to be able to tell which ones are not peaches, first of all, that are rocks, say, and which ones are already rotten. My dad had a summer job one time where he was the banana inspector, and he had to pick out the bananas that were already yellow, because by the time they shipped from there to market, they would be brown. He said it was the most boring thing he's ever done in his life. So this is supposed to automate that. And again, underlying it is this basic problem of establishing correspondences between pixels in one image and pixels in the other. Now note, part of the cornflake box is covered up, but each and every one of you in the room can tell that the cornflake box that's on the right is present in the image on, well, on your, yeah, it's present in the image on your left. So it's partially occluded, which means that we cannot simply look for an entire patch of pixels that's this big that's got all of the cornflake box in it, because we'll miss it. So in order to get around this occlusion problem, what we have to essentially do is look for bits of the image that look like bits of the cornflake box. So it shouldn't be hard to figure out that if we can find a block of pixels that are about this big that correspond to this region, and another block of pixels that look like this part of the image, then we should be able to tell that the cornflake box is there. Again, finding correspondences between local regions in one image and local regions of the other. Any questions about the applications at this moment? Good. Okay. So how would we go about solving this problem of identifying that there's a block of pixels in one image that correspond to a block of pixels in the other? Well, the simplest thing we can do is called scanning. And what it does is essentially you scan through the image with a block of pixels that you think is about the right size to match something that's over here. So let's just say, for the sake of argument, that I know I'm looking for this particular block of pixels from the cornflake box. Well, what I can do then is scan a little green box like you're seeing there across the image on the left, and ask myself whether that block of pixels, yay or nay, does or does not look like the block of pixels on the right. See, does it look like that? No. Does this block of pixels look like the thing on the right? No. Does this one? No, and no, and so on and so on and so on, until eventually my scanning box goes through the image and eventually lights itself right here, and then ding, 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 I have found the block of pixels that looks like the one from my model. So let's think about, you can probably already guess why this is not such an advantageous approach. It takes a really long time. So it appears, unless you do anything that's more clever, that you actually have to scan through the entire image, looking at every location in the image in turn, for every block of pixels on the model that you might be interested in finding in the image. So it's exhaustive, which means that it's slow. But on the other hand, it's exhaustive, which means that you can't miss anything. So if there exists a spot in the image that has the thing that you're looking for in it, you'll find it, because you are eventually going to scan over it with that moving green box. So it's kind of foolproof in that sense. You can never skip over a part of the image that has the right answer in it. But it's slow. And in fact, another problem that's a little bit more subtle is that there are usually too many correct matches. And what I mean by that is that, sure, when the block of pixels is in exactly the right position, then you will get a pretty excellent score that it looks like the thing that you were looking for over here. Unfortunately, what also happens is that when the block of pixels is offset by just a few pixels, you still get a pretty good score for it looking like the thing you were looking for over here. And similarly, if you shift it over this way, it'll still look not perfectly, but pretty good like the thing you were looking for on the right. So what you end up having to do is a post-processing step where you essentially do something like non-maximum suppression, which we've talked about twice already, where you take a big kind of extended area of pretty good matches for something, and you shrivel it down and you shrivel it down to just a point. So it's an added pain that most people don't consider when they implement a scanning algorithm like this. Now, let's imagine an alternative where instead of scanning exhaustively through the entire image, I first do a pre-processing step where I identify spots in the image that are, here's that word again, salient, aka interesting. Here are another few words that you will find if you read papers and books about this. They sometimes call these locations iconic or representative. They're also sometimes referred to as key points. And the etymology of that word should be clear. They are key to your interpretation of what's in the image. So let me just say that if I have an algorithm that will detect these interesting regions before I start looking for my block of pixels that I'm interested in, then I can reduce the imaging data to a much sparser set of pixels. And if I find interesting regions here, 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 and so on, then my problem of finding locations in the image that match my block of pixels on the right becomes a whole lot faster, because all I have to do is ask myself, if that interesting region looks like my thing on the right, no, no, no. And eventually I will hit the location in the image that matches the thing on the right. But the point is that it took far fewer comparisons for me to do so, assuming that my interesting point detector algorithm doesn't do something stupid, like light up the entire image with so-called interesting points. So if it actually does a pretty good job of taking a dense image, in other words filled in, and reducing it to a sparse set of locations, then I will actually find my region in the image much faster. So that's one of the pluses, is that it's faster. And also we don't have this problem of non-maximum suppression, where instead of having one spot in the image that matches one spot in the other image, we kind of have this smeared extended region of matches. So it's not always reliable, and this would be your failure mode right here, where your pre-processing step that detects these interesting regions tells you that the top right of the cornflake box is not actually all that interesting. So if it's not interesting, you can't match it, because that was your algorithm. So just by merit of that fact, you are not going to be able to match this region to anywhere in this image, or you're actually not going to find the right one anyway. So it's not always reliable. That's kind of the pitfall. And you also have to come up with a solution for this kind of ambiguous question of what does it mean by, what does it mean when I say salient? What does that term mean? Well, I'd like to posit my own, what I think was a pretty good answer to this question from the paper that I referenced in the beginning of the class. There's basically three properties of an image region that are important to consider when you want to call it, when you want to decide whether to call it salient or not. First of all, salient regions should be rare. So remember I said that if your interesting point detector papers the entire image with nothing but interesting regions, then that automatically makes them not interesting. So interesting essentially means that they are sparse, that they occur rarely. They should also be repeatable, which means that if you take the same object and you photograph it 50 different times from slightly different points of view and under slightly different lighting and at slightly different times a day and with slightly different models of cameras, you should get the same interesting regions out each time. And if, by the way, if you can do that, then you essentially solve that problem that I showed you just in the previous slide, where there's no interesting region on the cornflake box, so you can't find your match against what is on your model image. And also it should be localizable, which is to say that they should be isolated, closed regions instead of extended, large regions in the image. So rare, repeatable, and localizable. And this just shows you kind of pictorially what those mean. The thing on the left is what you want. You have isolated regions when it's rare. It doesn't paper the whole image. And going the other way is asinine as well, where You essentially say that nothing in the image is interesting. It's not what you want. Here's repeatability. The thing on the top, is repeatable. You should be able to see that there's a green triangle on the left that corresponds to the same part of the object as something on the right there. And on the bottom is not what you want, and it leads to that problem of not being able to find matches. And it should be localizable, which is to say that, well, this just gives an example of that. So if there's an interesting part of the region of the image that's right here, it should always say that this region is this size. It shouldn't kind of oscillate between being small in one image and being large in another image. So rare, repeatable, and localizable. So there are some examples of salient regions in the literature, and we talked about one in the very beginning of this class, which is that if you run a Harris corner detector on an image, what you get out is essentially interesting regions, which is kind of nice because it's such a simple algorithm. And sometimes they're rare and repeatable and localizable. And in fact, if you run it on this kind of an image, where there actually are honest-to-goodness corners throughout the image, probably if you take this photograph from different points of view around this building, you will get similar interesting regions across images. Because they conform to what the Harris detector wants to see. It wants to see really corners in the usual sense of corners. And sometimes, if you give it other types of images, such as the kind of a blown-up image of a rock, like that one, then basically the entire image will light up as being interesting. So it doesn't have that rare quality to it. And in fact, there's no mechanism inside the Harris corner detector that encourages a certain density of corners or a certain number of corners. So if the entire image is busy in this sense, then the entire image will appear to be interesting, according to your Harris corner detector. This is another kind of interesting region or interesting feature in the image that has come up a lot, and it has to do with scale. So let me explain what I mean by scale. Imagine that the thing on the bottom here of this graph is one of those one-dimensional plots of image intensity. So if you remember the brain image I showed you, I picked one kind of strip going through the image and I plotted the intensities from bright to dark to bright. This is another one of those. And now imagine that what I do is I smooth this thing over and over and over again with a Gaussian filter, which, as we know, removes image noise, it suppresses high frequencies from the image, and it makes edges less localizable. And furthermore, let's say that I start by convolving the image with a Gaussian whose width is very, very narrow, so it doesn't do very much smoothing at all, doesn't remove very much of high frequencies at all. And then I widen the Gaussian a little bit and convolve again. As you can see, if you go from here to here to here, you're making the whole thing more smooth, you're removing more high frequencies, you're removing more noise. And if you keep doing that, widen the Gaussian and convolve, widen the Gaussian and convolve, eventually you will essentially remove all hint of any interesting content out of the imaging data altogether. But if you actually kind of pick one location in this strip of image and follow it as it goes from the original image to the most smoothed out one, what you will find, if you look at it for a while, you will find that there are features of this image, such as this drop-off here, that live for a while, and eventually they essentially die out as you go from fine-grained or very, very narrow smoothing to wider and wider and wider smoothing. So the reason why this is referred to as scale, and why this diagram is referred to as a scale space diagram, is that scale can be thought of as a synonym for level of detail. So if you look at an image from a certain scale or from a certain level of detail, and if you look at it from far away, basically most of the features in it or most of the interesting content will be removed. And that corresponds to the smoothing at the top. But if you look at it at a very fine level of detail, you see more and more fine-grained features in it. So So one idea is that we can basically look for features in the imaging data that survive across a large set of scales. And actually what happens is something even more interesting, which is that if you have one step edge like so, and another one like, it's a little bit hard to see, but this one here, what eventually happens is that they join together as you do more and more and more smoothing. And that's shown here, where, let's see, this guy corresponds to this thing. And what this is telling you is that that edge there is alive, 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 and then whoop, eventually it merges with the guy that is, with the edge that is over here. So you can imagine that one way to think about what's interesting in an image is to say, what can I see in the image across many different levels of detail or across many different scales? Is it present when I zoom in and look at it very, very closely? And is it still there when I pull it very far away from my face and squint? So this is one idea about how to define interesting regions in the image. It's image regions that have edges that exist across a wide range of these levels of detail. So this can be useful because edges are often rare, so it has that rare quality to them. It's usually not the case that an image is just filled with edges. If something is present at a wide range of scales, that suggests to you that it's repeatable. So kind of by construction, any edge that I can see across a wide range of scales is going to be repeatable if I vary the scale of my image. So if I zoom out of that object and take another photograph, I should be able to see most of the things that are present across a wide range of scales. And edges are often well localized. However, we talked about why that can be problematic if you do too much smoothing. But now, what I've just told you, you don't really get image regions per se. Essentially, what you get is a labeling of each edge pixel telling you how much range of scale it exists across. So it doesn't give you kind of an extended image region in the usual sense. So you have to find a way around that. Okay, but now this idea of scale is built into the approach that I referenced in the beginning of the lecture by these two guys named Kadir and Brady. So the key assumption of this approach, basically they combine looking at features across many scales with one other idea called entropy. And I'll explain what I mean by that right now. So the starting point for these people is that they say, well, look, most regions of the image can be described in terms of a very simple model. And when I say model, what I mean is essentially an explanation for the contents of that image region. So most of the regions in the image, like this square over here, can be explained in terms of a very simple model or in terms of a very simple explanation, which is to say the image pixels are, for the most part, just red. So there's a very small number of colors that are involved in that image region. So it's almost monochrome or almost flatly colored. There's a few dominant colors or a few dominant intensities. Other regions are simple in the sense that there's a small number of dominant edge orientations. So for example, if you take a little square around right here, or kind of a small region like this, what you'll find is that there's a very simple model for that image region too, which is to say, okay, for the most part, the pixels are flat, but where we do have edge pixels, they are in one dominant orientation, that one. And you can think of other examples of this where you can isolate regions of the image and tell a simple story that, you can basically tell a simple story that tells the entire story of that image region. And that regions that break this mold that you cannot tell a simple story about are rare, that they don't happen that often. So that's basically the key assumption of this work. And I think if you actually go through this exercise of going through every region of the image and trying to come up with a simple story about how you would explain its contents to people, I think you'll find that this is true. So now let's try to squish this idea into some mathematics. Let's imagine, to do this, that we form histograms. Hopefully you're all familiar with what a histogram is. What we can do in the case of trying to tell the story of this red patch here, if we want to figure out exactly how simple the story is of this image region, what we can do is form a histogram of all of the colors of the pixels in the region. So each pixel casts a vote into one of these bins, where the bins are ordered. This is a little bit abstract, but where the bins are ordered by hue, so that, for example, the bins down here correspond to blue, these ones are green, these ones are red, these ones are yellow, and these ones are maybe cyan. So for this little region, what I can do is basically put each one of those pixels into the bin that corresponds to its color. And lo and behold, you will find that this histogram has a characteristic shape. It has a big peak in it. It's not spread out. It doesn't have a wavy shape to it. But it looks like it just has one big spike. And similarly, if I were to go to this image region up here, which I didn't really show you in one of the slides, and instead of having a histogram of hue, I have a histogram of edge orientations, such that each edge pixel votes for what orientation its edge is, you would find a similar spiky appearance to its histogram. Meanwhile, if I look at another part of the image where I do not have one dominating color, I actually have some yellow and some red and some green and a little bit of maybe brown, and you make the same kind of hue histogram as you did in the previous slide, you'll notice something quite different. That in fact it doesn't have this spiky appearance, it's more flat. And one way to rephrase that is to say that if you were to have to, if I were to present you with a image pixel and you didn't get to look at it, and you had to guess what color it was, without even being able to look at it, for this image region, it would be tough. A lot of the times you would get it wrong no matter what color you picked. But for this image region, you would actually do a pretty good job if you just guessed red, 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 red all the time for every pixel. The more mathematical way to say that is that the entropy of this histogram is very, very low, and the entropy of this histogram is very, very high. Entropy is basically another term for uncertainty. The idea came out largely from the signal processing literature and from communications theory back in the kind of, I think, the 40s or so. But you should kind of get the intuitive idea that for any given pixel, its color, unless you are able to look at the pixel, is uncertain in this case, and it's fairly certain in this case. And it turns out that we can quantify this thing called the entropy. It's mathematically well defined. I'll let you look at the formula, but the formula is not really the point. The point is that I can summarize this whole histogram into a number that is very, very low for this guy and very, very high for this guy. It's called the Shannon entropy. There are other entropy measures. They're all trying to do the same thing, which is rate a histogram as to how spread out it is or how peaked it is. So we're going to say that an image region is salient if it has a high entropy feature distribution, which is to say there is no simple story for it. Or in other words, if you don't get to look at the pixels and you had to guess for any given pixel what its color was, what its edge orientation was, etc., you wouldn't be able to guess very well. So let's go back to our three different criteria: rare and repeatable and localizable. So if your simple local model is accurate and it does a good job of summarizing what was in the image in the first place, then yes, these regions are going to be relatively rare. And there's no proof for why these things are repeatable, but empirically they tend to be fairly repeatable. If you were to take that same photograph of the cornflake box and rotate it in a few different directions and ask for these high entropy color histograms or high entropy edge histograms, you'll find that the same parts of the object light up as you move this thing around. And I'll show some examples of that in a minute. And they're localizable by construction because we're forcing it to be a localized part of the image. So what we're going to do for this algorithm is search for, basically for each level of detail, like we talked about for the edges, and for each region in the image, we're going to evaluate its entropy of its feature histogram. And by the way, you have to pick whether that feature is color, edge orientation, or something else. So we're going to evaluate the entropy of those feature histograms across scale and across space. And then we're going to do this trick that's in the second step of trying to figure out how localized that peak is across scale and space. And then provide the user with the scales and the locations of those peaks, and those are going to be our salient or interesting regions. So the second step is important because it guards against some accidental peaks in extended or high entropy textures. So basically, if you use something like edge orientation, basically this entire wooded part of the image is going to look interesting. And so what's going to happen is that if you start at this location in the image and calculate the entropy in its edge orientation histogram, it's going to be high here, high here, high here, and it's just going to be perfectly flat across a wide range of scales and across a wide range of space. So if you want to find a region that is interesting and localizable, you really want this thing to have a more well-defined peak. Otherwise, it's really ill-defined whether you should say that this region in the image is interesting or whether this is. And this just tells you the same thing in another way, that basically if you have an image like this, we want to be able to say that that nothing in this image basically pops out from the background. And so if I have this gray region, I'm trying to figure out, well, is this an interesting region? It really doesn't matter if I make it this big or smaller or larger. It's all kind of equally interesting across all of those scales. So here's a result. On the left, what we're doing in this movie is, in each frame, identifying these interesting regions based on edge orientation histograms, the entropy in those, at a fixed given scale. And what you should see is that it does a fair job of doing something intuitive in the sense of always saying that the moving cars going through the intersection are interesting parts of the image. I think if we looked at the video, we would probably say the same thing. But it does some other things that are not so intuitive, which is that, for example, the light pole's not going anywhere. It's not doing anything. And it's not especially interesting, but what you note is that there are these parts of the flagpole or light pole that kind of become interesting and become not interesting for no apparently good reason. And then, oh shoot, I thought I had a video here. No, I guess not. What you see on the right is demonstrating this idea of detecting these interesting regions across multiple scales. So what you'll see is that not all interesting regions of the image are the same size. That there are these kind of large, extended, interesting regions covering the cars, and there are little, more isolated ones, like I think the one at the top of the light pole is a pretty good example of a little region that is nonetheless pops out from its background in some sense. And the reason why it's able to do that is because we're allowing it to select regions at different levels of detail. And this just gives another example where not only are we doing this pre-processing step of saying, find me all the interesting regions of the image, but then we have a step after that that tries to cull out regions that are interesting but nonetheless do not look like automobiles. So as you can see, it does a fair job, with some exceptions over here, of finding interesting regions that are just on the cars. So this gives you more of a sense of the overall application of this, what you would do with interesting regions once you found them. Here's not sure why that is so fast, but I think it's because I'm using a different version of Keynote than I did last year. But if you watch it a few dozen times, hopefully you'll see that there is this problem in the background, which is a demonstration of what I tried to describe a couple minutes ago, which is that basically the entire tree in the background looks like one gigantic extended interesting region. If you don't have this thing of saying that the peaks in your interestingness measure have to be localized in space and in scale. So if you do that and you say that you were going to force it to pick one scale and location where it's interesting, then basically most of the tree goes away, although there's still some problems, as you can see. That is, I'm going to have to look at that. The interesting thing is that the other video ran at exactly the same speed as it always does. So I'm not sure what the problem is. And this, again, is it's actually a challenging case of trying to not only identify interesting regions in this video stream with all of that junk going on in the background, all that foliage, but then afterwards reduce it so that the only interesting regions that are left look like this person and don't look like foliage. So you're trying to cull out the regions that are interesting but don't appear like people. Here's what happens. Again, one of the key criteria that we have is that it has to be localizable. And hopefully this is easier to see now. Or, sorry, that it has to be repeatable, which is to say if you take an image of the same object under different conditions, you should get the same regions. And it's a little bit difficult to see, but if you take an image of the Anison box close up and then zoom out and take another photograph, you'll get more or less the same regions. And in particular, I think the ones that you can actually tell are these two big circles right here. There's one here, and then there's one like so. And you should see that, roughly speaking, there are two big circles here that are more or less covering the same part of the box of medicine. A similar thing happens if you take the box of medicine and you rotate it. You get more or less the same interesting regions over again. And again, I'd point your attention to the two big circles that are overlapping over here. And these cover more or less the same location in the object, which is to say that if the image on your left was in your database or was your model, and the image on your right was an image of medicine boxes going by on a conveyor belt, you would have a good chance of detecting that the object was there just based on this sparse matching using interesting regions. If you change the brightness level overall of the image and rotate it, again, you get fairly repeatable results. And I'll let you kind of examine that to look for places where that's true and places where that's not true. I guess right around the guy's Adam's apple at the very bottom of the image, you can see there's a problem there where it's there on the left and not on the right. But and here's a very concrete example of an application, which is in fingerprint identification. A lot of times algorithms for fingerprint identification start with a step that is related to finding salient or interesting regions, and then calculating various statistics based on where those regions are and how they're related to each other to determine matches between one fingerprint and another. So in conclusion, if you can find salient regions across space and scale, then it has the potential for making a lot of very useful tasks much faster. We're proposing here that salient regions are defined by the fact that they are rare, repeatable, and localizable. Those are your three criteria to keep in mind. And in this particular approach, we're saying that salient regions are ones that don't have a simple explanation. They're not well described by one single color, by one single edge orientation, and so on. And then the math is just a way of kind of fitting that notion into something that's operational. Any questions? Okay, great. I have my office hours now, and then also next lecture is Wednesday.